Come up with Robert, and put your phone there if it's not there already. Michaela?
Here.
Quinn? Julia? Daniel? Other Daniel?
Here.
Olivia?
Here.
Samantha? Julian? Claire?
Here.
Allison?
Here.
Lauren? Granville?
Here.
Samantha? Bernice?
Here.
Nicole?
Here.
Cassandra? Annika?
Here.
Christina?
Here.
Decus?
Here.
Alexandria?
Here.
Annabelle? No, she's not here. Mayan? Ariana?
Here.
And Leah. So, the plan is, maybe a bit ambitious, but the plan is for Tuesday to do this lab. So I want to talk about the lab, but also about the lab format. Many of you might be used to doing lab reports where you gotta write materials, you gotta write out procedures, you gotta write out the questions. We don't do that. Okay, there's no reason to write out something that you already have written out for you. The only thing that goes in the lab report is what you did, and what you're doing relates to the objectives of the lab. So, title of the lab should be in the middle at the top of the page, and it's not chemistry lab, it's this title, at least for this lab. Separation of a mixture by paper chromatography. Notice that separation is spelled S-E-P-A-R. Don't spell it wrong, I mark spelling. To the right of the title, your name and your partner's name. I don't care whose goes what on top because you're both handing in the same lab report. So there'll be one lab report per group of two. And then over on the left is write the date the lab was done, not the date it was handed in, and the block. The problem or aim could also be called objectives. And every lab handout you'll get has objectives. So there they are. You can write them out, okay? Data and observations. Part of your data and observations is your data table that should be prepared prior to coming to class. All right? There is a sample data table in the lab. Here. Don't photocopy this and then white out the complete in your notebook. Build your own. Don't put table 4 in it, that's just for reference sake. Okay? There are a plethora of straight lines on here, so use a ruler. I don't care if you do the data table on a computer, you can if you want to. Just make sure that your partner's data table is in what you did, photocopied. Okay? So if it looks to me like one data table was photocopied 4 or 5 times, I don't know who did the data table. The purpose of you doing the data table, in part, is for me to convince myself that you know what it is you're about to do. If all somebody does is hand you a data table for a lab you're about to do, you may have no idea about the hazards or dangers or considerations for the lab. Now this lab is not a dangerous lab. The only thing you gotta worry about is a test tube breaking and getting glass in your eye. So we are still using goggles, but there's no toxic chemicals. The chemicals we're using are water and food coloring. Food coloring is water soluble, but it still doesn't come out of clothes that easily. So there should be no issue with that because we're going to be applying the food coloring with thin stirring rods. Okay. Table 3 down here, or yeah, it'll require a little bit of explanation on my part, but I'll get to it before the end of the period. Okay. The other thing that goes in the data and observations is anything that occurred during the process of the lab that you might want to write down, like observations that were occurring, for example, on the chromatogram when the color separated. And you'll notice on the back side of the third page, observe what happens when your sample spot at the water moves slowly up the paper as a result of capillary action. So when there are references like that in the procedures, write that down in data and observations. Obviously, part of the data and observations is C data table, but also the observations that were made over the course of the lab proceeding, okay? Collecting data is really all you have to do in the lab period. You don't have to write the lab report up. the lab report will never be due the day after the lab. The day after lab is solving problems associated with the lab report. And there's some calculations, and we'll go through those, but maybe between the time you did the lab and the time it's due, you're not sure about how to do these calculations. We'll solve that the class after the lab. The class after that is when the lab report will be due. One report per group, 2 data tables per lab report. Now, if there's an odd number of people, then that means 1 group of 3. You can't do the lab by yourself, and we're not going to have any more than one group of 3, because 2 groups of 3 is 3 groups of 2. When you come to the lab on Tuesday, there will be, for each group of 2, there will be 3 test tubes, either sitting in 3 separate Erlenmeyer flasks or in a test tube rack, okay? The apparatus that you have to arrange that in is shown for you on the bottom of the front page of the lab handbook, okay? And I'll go into that. Most of the labs we're going to be doing will not involve calculations, but this one will. So underneath that in observations. In most cases, there'll be no calculations required. However, if they are, you can't include them in data because calculations are mathematical operations done on data. Whenever calculations are necessary, all the work should be shown. Now, in this particular lab, there is one calculation you kind of have to do over and over again, called an RF calculation. But you don't have to show me every single time. Just show me an example of each of the different calculations you did. Very straightforward. But you don't need to do that in the lab period. The lab period is just for collecting data. And once you've collected your data, once you've recorded everything, then clean the stuff up. Make it look at the way it looked when you got there. The only thing that's going in here is water, but we'll probably have some test tube brushes to brush them out, given the fact that there's also going to be food color. Okay? Put your goggles away. When all of that's done, then you and your partner can start writing the lab report out. I don't think the lab will take an entire period, but as far as I know, Tuesday is a regular day. So there shouldn't be any issues finishing this particular lab. And I'll go through the procedure with you in a few minutes. At the end of every lab, there will be questions. On here, they're labeled analysis of results. So there's actually 2 parts to the question section. There's these, and there's also follow-up questions. If I don't want the follow-up questions done, I'll let you know. But in this lab, I will want them done, and I'm going to go through some of them today. Okay? So let's talk about chromatography. Chromatography is the last separation technique we're going to discuss. Remember the ones we talked about last class? We talked about filtration, evaporation of dryness, distillation, solvent extraction, recrystallization, centrifugation, and all of those took advantage of one property difference with the mixture components. It might have been boiling point, it might have been size, it might have been solubility, concentration, density. But chromatography relies on 2 different property differences for each component. So if you look at the top of the first page, chromatography is one technique used by chemists to separate mixtures of chemical compounds in order to identify or isolate their components. In chromatography, mixtures are separated according to the different solubilities of the components in liquids, and then rather than or, write and their adsorptions on solids, or and or their adsorption. Notice it doesn't say absorption. Adsorption means to stick to, adhere to a surface, okay? So, in a nutshell, each group of 2 people will be doing 3 of these, 3 chromatograms. The first part, the first of 3, will be each group does one of the 3 primary colors, red, yellow, or blue. So at the beginning of the lab, I'll just say one member of each group put their hand up. I'll look at you and go blue, yellow, red. That's the first chromatogram you run. Then everybody's going to be doing green, and everybody's going to be doing an unknown mixture. Okay? There are two people in a lab group because one person has a job to do and the other person has a different job. One of the members of the group will be trimming each of 3 pieces of chromatography paper to the dimensions described on the top of the front side of the second page. Setting up. Obtain 3 large test tubes and 3 Erlenmeyer flasks. You can use Erlenmeyer flasks, and we have enough. You can use test tube racks. We even have these, which work actually even better than Erlenmeyer flasks, just specimen jars. And these test tubes, they just fit just perfectly inside them. It doesn't matter what you use as long as it'll hold it vertical, okay? The sizes of the pieces of apparatus are important for the rest of the procedure. Place a test tube in each of the flasks and label the test tube A, B, and C. You don't have to worry about A, B, and C to be able to tell them apart. In the bottom of each of these test tubes, one member of a group is going to put 2 centimeters of water. It's important that it's not any deeper than 2 centimeters of water, because when you put the chromatography paper in there, you don't want it to be sitting in water that's too deep. As weird as it sounds, what has proven to be the most difficult part of this lab is drying the inside of the test tube. If you take a paper towel and stuff it all the way in, you won't be able to get it out. So when you're drying the inside of the test tube, you don't want the inside walls of the test tube to be wet, because that's going to affect how the chromatogram develops. So make sure when you put the paper towel in, you leave enough of it sticking out of the top so you can pull it out. It doesn't sound like rocket science. It actually sounds more like advisory. But you'd be amazed how difficult the students have with that little procedure, okay? So as long as the inside of the test tube is reasonably dry, you guys want me to show you that again? Are you okay with it? Then the paper can go in there. You don't want water coming on the side because it'll affect how the chromatogram develops. So one member of each group is going to do 3 of those. The other member is going to take each of the 3 pieces of chromatography paper, which is just dense filter paper, but it's made for chromatography. And then you're going to measure a 4 centimeter length from one end, and I'm just eyeballing 4 centimeters here. And then you're going to trim the bottom of the chromatography paper to a point, and then using a pencil, not a pen, you're going to draw a reference line. What comes off the end of a pencil is carbon, it's graphite, and it's not water soluble, which is why we want that reference line there, because we want that reference line to stay there and not move. Now each group is going to do 3 of those. One for the primary color they do, red, yellow, or blue. One for the green, which everybody does, and one for the unknown mixture, which everybody does. Once all of the test tubes are ready, with the 2 centimeters of water and dry, and all of the chromatography strips are ready, drawn to a point, not 2 centimeters, nor 3, but 4. The idea is the 2 centimeter depth of water is going to go only half the way up that point. You don't want the reference line sitting in the water because the sample spot that you put in that reference line is then going to dissolve in the water rather than waiting for the water to pull it up. Once all of those are ready, don't put anything in there yet, then you take your 3 pieces of paper, which is the only thing that leaves your desk, not the test tubes, and then you're going to apply the appropriate spots. When you apply the spot, you're going to be using a little glass stirring rod. Now, sometimes people aren't sure how big the spot's going to be when they dip it in the sample of food coloring, and that's why there'll be some paper towels at each station just to practice. The size of the spot relative to the paper should kind of look like that, okay? So you want the dot to be big enough that it'll separate, so bigger than the head of a pin, but smaller than a pizza. You don't want so much of it to be on there that it just soaks into the water. So the sample spot It shouldn't be a problem because you're applying it with a stirring rod. So you get a drop of that food coloring, and then you carefully apply it to the center of the reference line. All right? So you wouldn't want it to be any bigger than that. You're going to have 3 of these, one with green, one with the primary color, whatever it is, and one with the unknown. Then you come back to your desk, and the paper is just wide enough that it'll sit suspended in the test tube. But you got to curl it a little bit. Don't crease it, just curl it, and then you put it in so that the point just touches the bottom of the test tube. And now, by capillary action, you guys have all cleaned up a spill with a paper towel. You see how the water spreads out. That's capillary action. The water now moves up the chromatography paper. The water is what we call the carrier or mobile phase, or sometimes called the developing solvent. It moves. It will continue moving up. And as it moves up, the components of the mixture, if it is a mixture, are going to be carried at different rates up the paper. The paper is called the stationary phase. The water, the developing solvent, is called the mobile phase. And as the handout tells you, chromatography has many applications, and then it goes, there are a variety of chromatographic techniques, but all share 2 features. A moving carrier phase, in this case it's the water. Mobile phase, carrier phase, developing solvent, same thing. It moves. And a stationary phase. And a lot of times chromatography is named because of the stationary phase. In this case, the stationary phase is paper. Okay? If what you put on there is a mixture, the components of the mixture are going to move at different rates based on 2 things. How well they dissolve in the mobile phase, and how well they stick to the stationary phase. So if the components of the mixture are really soluble in the mobile phase, and they don't stick to the stationary phase that well, they're going to move pretty far. So the lower the solubility in the mobile phase, and the less they adhere to the stationary phase, the more they're going to move. The less they dissolve in the mobile phase, and the more they stick to the stationary phase, the less they're going to move. And you'll notice in the first paragraph it says, and or their adsorption on solvents. Adsorb means to stick to, all right? Adhere to. So those are the 2 properties. How well they develop in the solvent, or how well they dissolve in the solvent, and how well they stick to the stationary phase. The less they stick to the stationary phase and the more they dissolve in the solvent, the farther they're going to move. The less they dissolve in the solvent and the more they stick to the stationary phase, the less they're going to move. Which means if it is a mixture, over time, you're going to see the components of that food coloring separate. Now, we call primary colors primary because they're not made of any more than one thing. So when you do your primary color, blue or yellow or red, you're not going to see separation. If it is a primary color, then there's only going to be one color moving up that chromatography curve. But if it is a mixture, you're going to be seeing more than one. And the longer you let it sit, the better the separation between the components of the mixture. How far they move, based on their solubility in the solvent and adhering to the solid phase, is quantified by something we call an RF factor. Now, Gary has decided that RF means retention factor. It does not. It means ratio of fronts, okay? And
Fronts.
let's say we have our
Fronts? Like the front of something?
chromatography paper here.
Fronts like...
This is all in the handout, by the way.
Ratio of what?
It's all in the handout.
Ratio
There's your
of what?
And again, you want your reference line to be
Front.
pencil,
Front?
because it doesn't, you don't want it to dissolve in the mobile.
Like the front of something?
So let's say you start the chromatogram, and let's say you did red, okay? So the red spot is there at the beginning. So you dip it in the water's gonna start moving. As the water moves, it's gonna pull that, so the red spot will not stay there. It's gonna move. The reference line will be there, but the red spot at some point will be up here. And it doesn't look as nice and horizontal as you see in the diagram. It's gonna look more like this. That's the water. The distance the water moves, the farthest the water moves, we usually label that D2, and that stands for the solvent. Okay? That's the carrier phase, that's the mobile phase. That's what's pulling this, okay? And that's gonna move based on how well it dissolves in the water and how well it sticks in the paper. The farthest the color moves, not to the middle of it, but right to the edge of it, the farthest it moves, that's D1. And that stands for the solute front, which is appropriate because it's the solute that dissolves in the solvent. Okay? The RF value is the ratio of these two things. So RF would equal how far the solute moved divided by how far the carrier phase, mobile phase, developing solvent moved. Okay? What do you think the maximum RF value can be? Based on that ratio, what's the maximum value in RF can be?
The length of the paper?
Sorry?
The length of the paper?
Well, regardless of the length of the paper, if these are the two things in the RF value, the distance the solute moved and the distance the solvent moved, what's the maximum that ratio could be? In other words, could it ever be bigger than 1? No, because the carrier phase is pulling the solute. The solute can't be ahead of what's carrying it. Now, could the solute front be right at the solvent front? Yeah, it could. As a matter of fact, if you look in your lab handout, if you look at table 4, the bottom right-hand corner of the front page of the front side of the last page, you see over there blue number 1? That's the RF value for one form, one accepted, safe food coloring that's blue. So if this was blue number 1, it would be right here, okay? It would be right on the solute, the solvent. In other words, D1 would equal D2, okay? That's the only way it could be 1. I mention that because if you look at Gary's diagrams, again, just proving that he does have it incorrect. If you look at his diagram, he measures from the center of the component. Measuring from the center of the component, let's say we measured, let's say D1 was to here. Could you ever have an RF of 1? In other words, even if this was right on the line, if that's where you're measuring from, you could never have D1 equal to D2. And clearly, you do. And when we use the word front, it means the front of the movement, how far it's going, not from the middle. Okay? I don't know if you guys can see, but you see the yellow separating from the blue? See that? The longer it sits, and sits undisturbed, like you don't want to pick it up and shake it. Once it's in there, leave it alone. So most of the lab is gonna be you sitting and watching the chromatograph. And 20 minutes is usually a good time, and we'll talk about what to do after that. In any event, with the primary color, you're not gonna see separation, okay? So let's say you saw something like that, right? And you measured D1, D2, and calculated the RF for that red. If you look at the tables that you're filling in, table 1 is what each group individually does, right? So color tested red, D1 in centimeters divided by D2 in centimeters. So you let it sit long enough or run, clearly it's evident that you're not seeing any separation. So the primary color will take the least amount of time. Write your measurements down, do the division. Notice an RF value has no units, the centimeters cancel. That goes on class data, which goes on the board. So I'll build table 2 on the board. Let's say there's 3 groups that did red, 3 groups that did blue, 3 groups that did yellow. Each of them put their RF values on the board, and then we're gonna average all the ones for the people that did red and blue and yellow. Which ideally should mean that the RFs we calculate for the blue and the yellow and the red are pretty accurate. What's table 3? Well, table 3 is devoted to the mixtures. Each group is gonna do green, which you may or may not know is a mixture, but you're seeing clearly it is, right? As a matter of fact, what qualitative evidence do you have that green is a mixture? It's separated into 2 different colors, okay? The data that we put here is for the green and for the unknown. Now, as you see here, it looks like green is a mixture of yellow and red. Correct? So when you do the table, notice it just gives you 1 row for green. You need as many rows as there are components in that mixture. So, I'll just explain to you a little bit about this table because some students are a little confused on it, okay? So this is green. So where it says component colors, yellow and red, or yellow and blue. So let's put yellow here, and blue here. And then each of those have a D1 and a D2 in centimeters. So this could be D1, that could be D2. Now, because they're on the same piece of paper, D2 is going to be the same, right? Because they're on the same chromatograph. So, this isn't yellow, but pretend it is. Let's say that's what you see, all right? Now, it may very well be that there's not white paper between them. As you can see here, the yellow is behind the blue, but there's no white paper between it. But each of those are on the same piece of paper, so each of them have the same D2. What's different is their D1s, all right? So whatever this is, and whatever that is, that divided by that will give you the column that says calculated RF. So from your green food coloring that your group did, the D1 for the blue and the D2 for the blue, and the D1 for the yellow and the D2 for the yellow should give you 2 RF values, all right? So you'd have an RF for yellow, and you'd have an RF for blue. That's the calculated RF, all right? But the last column is what a lot of students are unclear on. It says component RF from table 2. Above the word component, just write average. In other words, we want to see, for example, in the green food coloring, if the blue in the green food coloring was the same as the blue in table 2. where we average class data. So with the group that did the primary color, if that ended up being, say, blue number 1, and then in the green was at the same dye. Well, if the RF's the same, it's the same dye. It might not be, because there's more than one blue that's been approved. But if it's RF equals 1.0 in the mixture, and it's 1.0 as a primary color, it's the same dye, okay? And all of the dyes, by the way, aren't here. These are some of the approved dyes. So let's say if you did red, and let's say when the class average came out, the RF was 0.82. One of the questions in the lab is, did any of the dyes used correspond to any of the approved dyes? Well, if the class average is 0.82, that's pretty close to red number 2, which is 0.81. So you said, yeah, it matched or corresponded to red number 2, okay? Now, it might not. Doesn't mean that you did it wrong. It might just mean that the dye you're testing isn't on this table, because remember, it only says some of them, but some of them might. Let's say you've let it sit long enough that you can see clear separation. And again, the longer it goes, the better. The water's not going to evaporate. This is going to keep moving. But once you've let it sit long enough that you can clearly say, okay, here's where the edge of the blue is, and here's where the edge of the yellow is. Especially if they're kind of mixed in the same vicinity. So what you see on that chromatogram is maybe more something like this. There's the blue, and the yellow is like here, okay? So, the lab handout suggests take the paper out and draw a line across it for the D1 with the ruler. If you do that on a wet piece of chromatography paper, you're gonna tear the paper. So yeah, take the paper out, but maybe just notch where the edge of the blue is and the edge of the yellow, the farthest that it goes. Now, when you take it out of there, it's still wet, so that it's gonna keep moving for a while, the solvent front. But as long as you have that and this, you're okay. Then you take your measurements. That would be D1 for the yellow, that would be D1 for the blue. Okay? Make sense? And once all that's filled in, that's all you have to do in the lab. The rest are questions. Any problems with that? Now, the lab is gonna be, we're gonna try to get it done Tuesday, so you got the weekend and Monday to look through this. It's not that complicated, but we're on short box here, that's why it seems like I'm talking fast, okay? The questions at the end would be these things. So let's have a quick look at some of them. Which of the colors you tested in part 2 of the experiment appeared to contain one or more of the approved dyes in table 4? Well, look at table 2 class results. So let's say the average RF for the red was 0.82, and you look at the table and it goes, well, you know, that's pretty close to red number 2. Then say, yes, red seemed to be red number 2 with an RF of this. Don't just say, yes, red. I'll write which red. Red number 2, more than one red there. Red number 3, red number 4. If it doesn't correspond to it, then say so. The class average or the dye we calculated did not correspond to any of the approved dyes. Some might not. And remember, try to stay within experimental error. If red number 2 is 0.81, but the average for the red in the class was 0.69, obviously it can't be the same dye, which is fine. Okay? From your results in part 3, that's where we did the mixture. What are the components of green food coloring? Support your answer qualitatively and quantitatively. Well, qualitatively, we saw the color separate, right? Quantitatively, we calculated 2 RF values. That's the quantitative data, all right? That's all it means. What can you conclude about the identity of the components in the unknown mixture? I'm not gonna tell you what the components are, because that's why it's unknown. But after you see the colors separate, you'll be able to say, well, the components were this, this, this. Qualitatively, that's what I saw. Quantitatively, these are the RF values I calculated. That's the difference between what you see and what you calculate. What might happen if ink rather than pencil were used to mark the sample line? Well, a lot of brands of ink are at least partially soluble in water. So if the reference line moves, it's gonna be two problems. Number one, there's no more reference line from which to measure, but number two, if it's gonna dissolve in the solvent, it's gonna contaminate the chromatograph, because there's more than just the food coloring moving. And the fact that graphite is not soluble in water means when everything's all said and done, the line is still there, unmoved, unchanged, okay? Why should green food coloring be classified in mixture when yellow, blue, and red should not? Well, some people say, well, it's not a primary color. Yellow, blue, and red are. Well, base it on your data. According to your data, green separated into component colors. Ergo, it's a mixture. Whereas red and blue and yellow did not. So they must not be mixtures. Therefore, they must be primary color. Every question that's asked in this part, go to your lab handout. Go to your data, okay? Look at what you collected. The follow-up questions are different. The follow-up questions ask you to apply the stuff, but not refer to your data specifically. So look at number one. I don't normally do this much for you, but this is the first lab you're doing. Identify the dye that appears in the chromatogram. I wish chromatograms looked that nice, they rarely do. Consult table 4 for RF values. The original sample was orange. So if the sample was orange, if that's what the color of the spot that down here was, and by the way, intuitively you can guess what the components of orange food coloring are. Anybody? Yellow and red, okay? So when you do the arithmetic and your ruler measuring this, you're gonna be looking for red number something, yellow number something. Don't you say red and yellow? So when it says identify the dyes, red number what, yellow number what? The only way you can do that is measure. Put your ruler right on the page. D2, there's D1 for that, there's D1 for that. And then do the calculation. And you should get red number something, yellow number something on here, okay? I like the next question. The next question is a great test question, ladies and gentlemen. I might even write this out verbatim for the first part of the question. A pharmaceutical chemist runs a chromatography test on a substance and identifies two of its components by comparing their RF values against certain standards. That's exactly what you guys are doing in this lab. If the two components have RF values of 1.0 and 0.41, and the solvent front has traveled 12 centimeters, that's the water, what is the separation distance on the chromatogram? So what is the question actually asking for? If we've got two dyes on the chromatogram, by the way, if I separated purple, it would be red and blue. That would be D1, and let's call that A. And that would be D1 for B. We're going to call that B. Okay? So what they're asking for is that difference, separation distance. How far D1 moved compared to D2. It might look difficult, but it's actually pretty straightforward. And there's more than one way to do it. So the separation distance would have to equal D1A minus D1B. Everybody agree with that? How far that solute moved compared to how far that solute moved, right? Now remember the formula for an RF value. that solute, A, has an RF value, RF of A equals D1 of A, or A, divided by D2. They're on the same piece of paper, right? So D2 is the same for both of them, right? The RF value for component B has to be how far that solute moved, B, divided by the same D2, right? Remember, this is what we're looking for. So let's express each of these in terms of D1 for A and D1B. So this means, if that's true, then that means, those three dots are in there, that means D1A equals D2 times RF of A. You agree with that? If that's true, then this equals that times that, right? Yes? Same thing over here. That must mean that D1B equals the same D2, because we're on the same piece of paper, times the RF of B. Right? So far, so good? Well, if that's D1A and that's D1B, let's just write it. That must mean that D2 times the RF of A, which is D1A. You guys want to join the class? Get lost. And we'll do the same thing over here for D1B. According to this, D1B equals D2 minus the RF of B. Then we'll just use the distributive principle of multiplication in reverse. This equals D2, remember it's the same for both, times RF of A minus RF of B. Right? That's the separation distance. Now, that's not the only way to do it, but it makes it pretty easy based on what they give you. So, if the two components have RF values of 1 and 0.41, that's what's inside the brackets, and the solvent front moved 12 centimeters, that's D2. Makes it pretty easy. 1 minus 0.41 is 0.59. 0.59 times 12 in centimeters is the separation distance. Right? Now, if that's a test question, do I need to see all this? No, I don't. But if you write that equals, that's a pretty straightforward way to get an answer. Now, it's not the only way. You can work it out individually and do a subtraction. It's just that's pretty succinct, right? Something else to note. Because every RF calculation has 3 variables in it, that means there's 3 ways to write it. So knowing this and this, I can get RF. Knowing this and this, I can get D1A. But knowing D1A and RF, I can also calculate D2, right? As many variables as there are, there's that many ways to write the equation. Did I go through that too fast? Make sense? Now again, I don't normally do these for you, but you haven't seen RF calculations before, or chromatography, so I thought I'd help. Number 3 is kind of obvious. A chemist performs an RF calculation, obtains a value of 1.2, and decides that the answer is unacceptable. Why? Why does that have to be wrong if you calculate an RF of 1.2?
Because D1 can't be bigger than D2.
Correct, but why not? Why can't D1 be bigger than D2? You know why, just worded it. into an answer, yeah.
Because the food coloring can't go higher than the water.
Really, but why not? Why not? What's another name we give the water? Carrier phase. It's carrying the solute, it's pulling the solute. The solute can't go any farther than what's pulling it, or what's carrying it. Okay? It's like pulling your little brother in a wagon, and you look back and he's gone, and he's up here. Okay? The whole reason this is moving is because this is pulling it. So that can't be, the solute cannot be ahead of the carrier phase, or the solute, okay? When you get to the lab on Tuesday, again, unless there's a dramatic change in schedule, I still think Tuesday's a full day. Don't bring your coats, don't bring your bags, just bring in what you need. You're gonna need a pair of scissors and a ruler. I know it sounds like an advisory session, but we're actually doing science. A pair of scissors and a ruler, and at least one pencil. The rest of the stuff I'll supply, all right? The chromatography paper, the test tubes, whatever you're gonna suspend your test tubes in. And if you make a spot and you think it's too big, and it is, I'll just give you another piece of chromatography paper, lots of paper, okay? There's no reason to rush. Don't poke yourself in the eye or break the test tubes if you can help it. But everybody will have to wear goggles because we are using glassware. All right? Now, that lab will effectively complete section 2-3. There's only one more section in this chapter, and that's something most of you should be reasonably familiar with. At the beginning of the year, I mentioned that I didn't teach most of you last year, so I don't know what most of you brought to your chemistry skills in that unit. Some of you may have had difficulty with formula writing and naming, but if I didn't teach you, I wouldn't know that. Only you know. Added on to that was the fact that it was done a year ago, more than a year ago. So, if you're one of those people that struggled with formula writing and naming, then it's probably a good idea to have a look sooner than later at section 2.4. If you look at the very first page of section 2.4, that warm-up should look pretty familiar to you. This is page 90. Where you've got the cations down the left, the anions across the top. Some of the anions are monatomic, one atom, some are polyatomic. But remember, if they're all ionic, you always write them in the lowest ratio, brackets when needed, so you should be okay with that. Now, if you're a little rusty, all the more reason to check your answers after you try these. Don't worry about the inorganic stuff. That's all you've learned up to now. You haven't learned how to write names for any organic compounds. Although Gary doesn't ask for that, and there's not much room in those little boxes, but if you can write the formula, you should also be able to write the name. And remember, from here on in, on every test you write, you're going to get that, and you're also going to get that. So there should be no issues with finding the right names, finding the right formulas, okay? The vast majority of section 2.4 is going to be reviewed. The only thing that you probably didn't see, well, I know you didn't see it because I taught it, is hydrates. Those are compounds that kind of combine ionic and covalent together. But I'll teach that. And I'm not going to teach it assuming that everybody nailed this stuff last year. I'm going to teach it. I'm going to go through it again. It's just I'm going to go through it in such a way that I'm assuming most of it should be reviewed. Okay? There's lots of practice problems here. There's lots of review questions. And as I said, if you were one of those people that knew they had trouble with formula writing and naming, the more of those you do, the better. And as always, do them and then check your answers, okay? some people who maybe didn't do as well in the first test as they had hoped. And more than a few have asked me, is there gonna be time for another test before the parent-teacher interviews? Well, obviously not. Parent-teacher interviews are Wednesday. We're doing the lab on Tuesday. But we will have a test before the report cards. I think the report cards come out the last week in November, so we will for sure have had a test by then, okay? I don't know why we have the interviews 3 weeks before the report cards come out, but I guess it would make too much sense to have the interviews after the report cards, okay? Is there anybody actually teaching today? You guys want to join the chem class? You had to think about it. Finally, I said no.
Smart answer.
So, the march of the second test should be on Power School before the report cards come out. We're probably not gonna do our next lab until chapter 4. Chapter 3 isn't really lab material, it's just content. And that's where we introduce the mold. And that'll be brand new. Inasmuch as some of chapter 2 is review, none of chapter 3 will be. And all the stuff we did in 1 where we did the multi-step dimensional analysis stuff, we're gonna weave that into not just chapter 3, but also chapter 4. Okay? Feel free to start reading some of 2.4 if you want. If you haven't picked your lab partner yet, pick somebody who you like, because you're gonna sit next to them for 75 or 80 minutes. Also pick somebody who you think can help you get a good mark on your lab report. And if you are a partner, be a partner. Like, split the work up. Remember, before you hand the lab report in, you should both agree that everything that's on there is what you agree upon. So if you break up the questions, like say you're gonna do question 1, 2, 3, your partner's gonna do 4, 5, 6, look at what each other has done. I remember working on my master's, that was the thing that annoyed me the most, was group work. There were 5 of us in a group, 2 of us did the stuff that we were supposed to. Then we looked at what the other 3 people wrote, it was rubbish. These are like teachers. That's not a sentence, that's not a paragraph, that's not how that word's spelled, that's not what that word means, that kind of stuff, right? Teachers. The fact that we were all gonna get the same mark meant that some of us had to do more work than others. You don't wanna be that kind of partner. So make sure if you're given us stuff to do, you do it well. And then when you show it to your partner, then they agree with it, and when you see what they wrote, hopefully it's as high quality as what you did. That's what it means to be a lab partner. Okay? Don't expect the other person to do all the work. And if, by the way, they do, if you're handing in the lab report and the other person did nothing, tell me they did nothing, because they'll get nothing. Okay? So, and if you're a terrible lab partner, no one's gonna wanna be your lab partner. And I won't force anybody to be a partner with a terrible partner. And that might mean you don't get to do the lab because you're a terrible partner. So cooperate. And you might as well get used to it because you're gonna have to do that in post-secondary too. All right? That's all I got for today, folks. Yeah.
For the tables, you said we can do it on our computer. That means we have to print out the data to do, right? Like,
If you
to
do it
hand
on your computer, you need a hard copy of it, yeah.
Okay.
It's just that I don't want one person to do a data table and then 14 people to use the same data table. So even if you're in the same group, do your own data table. All right? I want them to look differently. I don't know who did it if they don't, okay? And that's what I'll initial at the beginning of the lab. And what I initial is what you turn in. You don't take it home and do it again. It's good lab technique to fill the data in as it's being generated. And then you just staple the data tables to the lab report, okay?
That's like my greatest achievement. I got my lab report signed last year.